All right, so this example is very similar to the last one. The big difference though is that there's this 40-pound weight hanging at the end of, in this case, a rope. So again, I could draw what I don't know if it helps or not, but here's the side of my building, here's the ground, and we have this 50-foot long rope, right, with a 40-pound weight at the end, right? So this is 40 pounds, right? And then the rope is 50 feet. But it's the same sort of thing where we're taking this rope, it's hanging over the edge of the building, and we're pulling the rope up onto the roof and raising this weight, okay? And now, obviously, we're just going to treat this weight as just a point in space. So we're going to say there's negligible length in this weight. All right. So we're asked to find how much work is done by lifting the rope and the weight to the top of the building. So again, I kind of like to use this idea of the variable force. Instead of slicing the rope into little infinitesimally small slices and adding up all of the work done to lift each one of the slices, I'm going to look at the variable force. So the initial weight of so we have the rope, right? And the weight. So the weight's hanging at the end of the rope. So we have 50 feet of rope, and we're told that the density of the rope is 1/2 pound per foot. And then we're going to add the 40-pound weight. 40 pounds. All right. If we add that all together, we get 65 pounds. All right. And so what's going to happen? Let's take a look at this variable force. All right. Now we're going to plot force versus the distance that we've lifted it. We're starting out here at 65 pounds. And so the difference here is that we have this weight hanging on the end. And so what's going to happen is you're pulling the rope, right, until you get to the end. So at the end, you're still going to have the 40-pound weight hanging there. And then suddenly it's just going to drop to zero, right? The force required is going to drop to zero once once we've lifted that weight up onto the roof. But this weight doesn't have any length to it. We're saying it's negligible weight, so essentially it looks like it suddenly just drops. When we get to 50 feet, right, and then we pulled the weight onto the roof, and so suddenly the force just drops. So we have this force function that kind of looks like this, where it's linear up until 40, from 65 to 40 until 50 feet, and then it suddenly just drops to zero. So let's find a function that models essentially, it's just this line, right? So it's 65 is the y-intercept, and then our slope is we're going down 25 and over 50, right? And times x. So essentially that's just 65 minus 1/2 x. So that's a function that models the force. And so if we want to find the work, we can just integrate that force. So we're going to get the integral from 0 to 50 of 65 minus 1/2 x dx. All right, so that's easy enough. We get 65x minus 1/4 x squared, right, evaluated from 0 to 50. All right, now we can just plug it into our calculator, and I got 2,625 foot-pounds. All right, because everything was in feet and pounds. So, and then we didn't have to, the rope was given everything's given in pounds. So it's already in terms of force. We didn't have to use the acceleration of gravity. So there we go. It's a very similar problem, slightly different, and also using the British Imperial system of units.